Good day, everyone. I am here to discuss to you the group theory. So in dictionary, group is a number of people or things that are located close together or are considered in class together. But in mathematics, group is a set of elements and an operation star, and together the set of the operations is denoted by this. That follows the following properties: closure property, associative property, existence of identity element, and the existence of inverse element. I am sure that these words are familiar to you. We had been exposed to this ever since grade school. The set of the real numbers and the operations of additions and multiplications is an example of a group. Let's go back to the properties of a group. Closure property. For every two elements A and B in G A star B is in G, that is our definitions and understanding the closure property. If you have been two elements from G, we applied our operations on these two elements, and the result of this is also in G. Then you will say that the operation is closed on that set. The parenthesis there is not necessary. I put it there just to help to improve the readability of the sentence. We can remove the parenthesis and replace it simply by a comma. Associativity. For any three elements of G, this is true. The symbol there, that means for all or every. Our understanding here is we will apply the operations first on AB, and then we will apply the operations on the result of this and this if this result is equal to this. Where we change the groupings of our operations, then we shall conclude the operations is associative in this set G.
And the other two properties are existence of an identity property. There is an element E and G. That is our symbol for there is or there exists. So, there is an identity element in G. Just that for any elements of G or for any A and G, E, star A is equal to A star E. And that is equal to A. This is the set of real numbers when we are working with addition. And you know that the identity elements in the for addition is 0. Why? Because real numbers added to 0 is equal to the real number itself. The set of real numbers under the operation of addition is an example of a group. Next is existence of the inverse element. For all elements of G, there is an A, inverse, and G. That is our symbol for the inverse element. We should not interpret this as 1 over A because this interpretation is true only when are working on multiplication. For each element of G, there is an inverse element in G such that A star A inverse is equal to E. This is happen in set of real numbers under the operation of addition. So what is the inverse elements for? Let's say for example number 5. In the set of real numbers when you are working with addition, well, the inverse element is negative 5 because 5 plus negative 5 is equal to the identity element for addition, which we know to be 0. Let us go back to the definition of group. An operation which is also closed or which follow the closure property is what we call binary operation. We can replace this by the word binary operation. We can just delete this property because by definition, a binary is an operation that follow the closure property. So in the other books, they define a group. In this way, it is a set of elements and a binary operation star that follow the following properties: associativity, existence of an identity element, and existence of inverse element.
So let us show the example of groups. Let us begin with the sets that are infinite. So a group is a set of elements and a binary operations denoted by this. This is how us denote the group. So group is always a set and the operation we apply on the element of that set. So it is a set and a binary operation such as these properties are satisfied: associativity, the existence of an identity element, and the existence of an inverse element. We shall identify if the set of the binary operation given in this table is a group. We have the set of real numbers and our binary operations is additions. Is it associative? Yes. Does it have identity element? 0 is the identity element. So again, yes, it has identity element, and 0, that is the identity element. How about the inverse element? Let's say for example, I have a real numbers. Does it have an inverse in the set of real numbers under the operations of additions? Yes, again. For example, your real number is negative 0.25. What must you add to negative 0.25 so that you will obtain the identity element? That is our definitions of the inverse. An element plus the inverse is equal to identity. And we know that to be 0.25, that is the inverse element for negative 0.25. And this is true for all elements in the set of real numbers. The set of real numbers under the operations of additions is a group. How about the set of natural numbers and the operations of addition? Again, the group is a set of an operations, in particular a binary operations and the operation of additions. Associative in the set of natural numbers. Yes. Does it have an identity element? None, so the identity element for additions is 0. But 0 is not to be found in that set of natural numbers. The set of natural numbers begins within 1, 2, 3, and so on. So the set of natural numbers is the same as the set of the positive integers, of course, does not have an integers element for its elements, and so this set of natural numbers under the operations of additions is not a group. How about this? This is a set that pertains to the set of whole numbers. The set of all numbers is the set containing 0 and the positive integers. This is the set of whole numbers. This group under the binary operations of additions, well, is additions associative? Yes. How about the identity element that is have identity element? Well, now it has because we included 0, but how about the inverse element? Can you, given a positive integers, can you find the inverse of that positive integers? Here under binary operations of additions, you need negative integers for that, and this one is not contain negative integers, so this not a group. How about this? The set of integers under the operations of additions. Yes, the addition is associative. We have the identity element, and now, yes, for every integer, we can find inverse also in the set of integers. The set of integers under the operations is a group.